Hi, this is Dan Gelbart with a short video of a scratch-built, very high precision lathe and grinder. The machine you're looking at can cut, turn and grind parts to a tolerance of 1 micron. For those of you who are used to imperial units, 40 millionths of an inch. So the first question which comes to mind is, why does a fellow need a machine accurate to 1 micron? And it turns out there's a lot of jobs where you need a machine like this, and I'll show you one example. Like here is a cylinder and a piston which is made on this lathe, and you can see that the piston is a complete sliding fit in the cylinder. It's completely loose fit. Now, if I seal off the air vent on top, you can see it's completely airtight. And another nice property, because it's so accurate, if I spin it, it spins freely as if it's on ball bearings, but it spins like a self-acting air bearing. And the same is true if I spin the inner piece. It will spin frictionlessly for a long time. So in other words, if you made a bearing like this bearing will never need lubrication and never wear out, because there is no contact between the inner part and the outer part. You can verify that with an ohm meter while they turn. It's the same idea as air bearing in a hard drive or air bearings in other self-acting air bearings devices. So this is one example of a part that, if to do it without a machine like this, you'll have to do it by time-consuming lapping. And it will be quite hard to get parts to fit to the tolerance. On this machine, it comes out like this, straight off the machine. So now let's go over the piece by piece how the machine is built, because it's actually not that difficult to build a machine like this. So this is a full CNC machine. I built the machine itself from scratch, but the CNC software was done by somebody else, an engineer by the name of James Madeley out of Vancouver, BC. The reason I couldn't use a standard software package is this machine is both a lathe and grinder and has some other special features, so I wanted to have a customized CNC package. So just let's go over the machine part by part, because there's a lot of parts of this machine which are different than a normal CNC machine, and then I'll run it to see how it works. So let's start with the chuck. The chuck is an unusual design. It's based on an extinct American design by a company called Skinner Chuck. And what is unique about this chuck is that at any opening it stays completely watertight. So when I open the jaws or close the jaws, the chuck will stay completely watertight. Now, this is done through drive pins, which drive the jaws, and the slot is covered with the jaw itself. Something else about this chuck is that because this lathe is designed for very small loads, I can grip parts through pins. So I can insert pins in the chuck, and I can grip parts on the ID or the OD without having to change jaws. So these pins give the chuck a very wide range, plus the regular gripping range of the jaws. So this chuck can grip anything from 0 to about 200 millimeter diameter. Something else which is different about this lathe is the tailstock. The tailstock, which is also on air bearings, of course, has a very long travel, all the way from the center being inside to the center being fully extended, about 300 millimeter. Now, this is interesting because it allows you to have a very long center distance for a very small lathe, because when the center is inside, I have almost 600 millimeter center distance, which is quite a lot for a small lathe like this, and even more if the bar can go inside. Now, all the parts you see ride on air bearings, as you'll see in a moment. I'm just not turning it on yet because air bearings are a bit noisy. So this floats on air bearings, this whole saddle floats on air bearings, the cross slide floats on air bearing, the main spindle and the grinding spindle are all on air bearings. Now, the only two parts here which are not made from scratch is the air bearings for the main spindle and the air bearings for the grinder spindle. which are surplus semiconductor machinery units, which are very cheap. You can buy those on eBay for a couple of $100 each, because a lot of machinery in semiconductors is air-bearing based. So the travel of the crosslight is long enough that I can move it forward and have enough room for lathe tooling, or I can move the whole crosslight back and I have room enough for the grinder. I can also use it in internal grinding. This grinding wheel comes off, as you'll see later, and I can put internal grinding mounts. For example, I can put a collet adapter here to hold with collets internal wheels, or I can put direct mount internal grinding wheels, which are threaded right on the spindle for more rigid wheels which you can go inside. And these are actually made to suit the job. So these internal grinding wheels are made to suit the job. And if you have a water jet cutter, they are very easy to make. All what you do is take a used up grinding stone and cut out any size of wheel you want with a water jet cutter. Then you just mount it with epoxy on the shaft. So and this way you have access to the full range of wheel materials which are available for external wheels. So now some other things I want to explain is how to get to the accuracy, because to get to 1 micron accuracy you need to start with a very, very good bed and very good spindles. I explained that the spindles you can buy surplus, the bearings, but I want to explain how you can make a bed accurate to a micron. So it turns out you can buy quite economically granite parallels, which is just a bar of granite which all 4 sides are parallel to a micron over the whole length, and you build up the bed by bonding with epoxy, 1 bar to another bar to form a T, and 2 of those T's to form a bed. Of course, when you glue it up, the whole thing is flipped upside down on a granite table, and there are very accurate spacers put inside. So once the epoxy cures, this surface and this surface are coplanar, and the gap here is accurate to a micron. Now, the glue joints are held under compression by these bolts. This big thing is the head of a bolt which holds the bed under compression, because like all adhesives, epoxy is very strong in pure shear mode, but it's very weak in other modes. So by holding the parts under compression, the only stress the epoxy is subject to is shear, which tries to cut them apart, but all other stresses are taken up by the compression on the bolt. Now this lathe has another feature that if anything goes wrong with the software, you can use it as a manual lathe with digital readouts. So these are the readouts for manual lathe mode, and that's about it. This is to lock the tailstock. Another item which is convenient is a built-in microscope, which you can place when you want to do small work. You can place here and see it displayed here. So this is a general overview, and now we start up the machine and we show it work. Okay, so now I'll just demonstrate one job, is cutting a thread. This is all programmed here to cut a thread. You can see through the video camera, looking down, a magnified cutting action. This is the tip of the cutting tool. So if we push the zoom, you'll see it cutting a thread. Here you can see the chip coming off, and you can see all the motions. Okay. Okay, now we can stop it. Okay, now we'll do a grinding example. So we program it for multi-pass grinding. One thing I forgot to mention before, that this chuck also has a run-out adjustment. These 2 screws allow you to zero the run-out of the chuck to 0, and that's very useful when you have to take a job out, do some operation and put the job back in. You can adjust the run-out to a reference surface to 0. So it's now set for grinding. We turn on the coolant, turn on the spindle, and start grinding. So it's still not touching the metal. In a few seconds it will start taking off metal. Notice that there is very little splashing from the coolant because the coolant flow is quite small. Now it's starting to grind.